Balint, Tahi, and Csongor Horvath of PPM Robotics. They're going to share their recent ROSin project, ROSWeld.
Welcome. Thank you for inviting us to this webinar. We are pleased to present ROSWeld. It's ROSin Europe FTP, and it stands for ROS-based framework for planning and multi-robotic welding. So, yep, that slide. Thank you. PPM is a Norwegian company. We are robot integrators, and we are focusing of emerging guys there in small and medium-sized enterprises, mostly for small series product, but sometimes you have to handle productions and also some bigger series also. We have an extended research network and partners all around Europe, and also in South Korea and Japan. Some of you from Pacific or America also met with our boss, Trygve Thomassen. So he's my boss, and we are engineers with Balint at PPM Robotics. Next slide, please. We joined ROS around 2 years ago, I think, and we have had a lot of good experience using it. That's why we decided to support the ROS Industrial Consortium and becoming an active member, also developing and participating in several events. We use them almost in every our project ROS now. We build up this knowledge from our previous projects, which contained grinding projects, milling, welding, or pelletizing projects. And currently we are developing technology for our partners for welding applications of huge structures, especially for hydropower turbine welding. Next slide, please. So ROSWeld is for one-of-a-kind production robot welding. You will see in the bottom ongoing process. This is from our previous project, but we developed further in ROS and made available for the community. We focused on usability and also enabling technology for multi-plus welding robot applications in ROS. So what we want to achieve to be able to plan, monitor, and control such projects, and utilizing the advantages of the ROS technology, but allow us to extend the capability of our softwares and also make it more compatible with different devices which we would encounter during integration in different sites. Next slide. So the ROSWeld is FTP project supported by ROSin Europe. We have 3 partners from Norway. We are the champion of the project PPM Robotics, and we are coordinating the project and developing. We have a partner, Mechatronics Innovation Lab AS. It's the catapult center for industrial robotics in Norway. They're located in South, and as their name suggests, it's an innovation lab for introducing the new technologies for the local companies. The other partner is Rainpower Norge. They are our main manufacturing and industrial partner. They are producing the hydropower turbines, and we are ongoing collaboration since 2006. The project started in last summer, And we finished the main development of the code, and currently we are working on the integration, the application in our partners. Next. So the main goal of the project to bring this kind of software to an industrial level, as the general also for ROS Industrial. We aiming to bring the planning, monitoring, and control softwares. We also integrating the components what we would use for welding. Some of them not integrated yet into ROS, so we delivering them as new, and also providing training materials as they'll be ready with them. The pilot project would be at Rainpower, and the generic setup would be implemented at Mechatronics Innovation Lab. Next, please. So how this software package is built up? We created the user interface in FlexGUI, which is our user interface. It will be it is enabled to plan the process itself. Then we use the simulation tool to simulate the motion of the robot in the virtual environment and enable collision detection. Then the control is integrating all the external hardware, including the robot arm, the welding power supplies, cameras, laser scanner, and devices. Input. Then we observe the process. We also store the process data for later analysis. We use it for ROSBAG and our ongoing other projects. And we make it modular to enable the replaceability of the components. For example, we implemented immediately 2 welding power supplies for and 2 laser scanners for this project. Next. So why we started to use ROS? Because we realized that integrating so many devices, it would be complicated. And we face that even though there are industrial standards, we have the challenges that not all of the devices using this whole range of standards. So we have to always tweak around. So therefore we realized that ROS is really good for us. So then we started to implement this. Next slide. And therefore we be using the ROS framework to use our project, and then we can extend this connectivity in a new high level. The user interface is FlexGUI. The simulation tool is MoveIt. You might be familiar with it. The ROSBAG storage. We also support multi-language interfaces because we target international projects, but sometimes we need the local languages. It's especially strong in Norway. They mostly requires the local language in the shop floor. Our delivered hardware components and drivers are the OTC robot driver. The OTC is the welding robot manufacturer, and they have a strong brand in Japan and in Europe. We developed a UDP-based driver to move and position the robot. It's constantly communicating with the server, sending status updates, and receive the commands from the ROS core. Then we implemented the OTC and Frenius welding power supplies. It's also UDP-based driver connecting to ROS core and sending out the welding process parameters. Then the sensor systems, we included the MEL211 and microphone laser scanners. They are laser by important to control the process and get feedback from the quality of the weld what we done. The IP cameras and the welding cameras are the vision system components, and we extended the control not only on the PC screens, but we enable to be portable and enable to be on tablets also. Next. So this is how we built our ROS system structure. The Flex GUI as the interface. So as the user interface communicating through the ROS bridge. Then we also have the ROSWeld core, which is developed in the project. And there you see other drivers, which is connected to ROS core, and the purple boxes are the actual hardwares and their interfaces to the drivers. Next slide. We use the following ROS tools. So the ROSWeld tools is consists of the purposes. It's including the welding projects, also providing the coordinate transformation to create the welding path, and also the simulation and the robot mode to be able to change between them, to be able to simulate first the project and the process, and then be executed on an actual robot. Then the Flex GUI is the front end. There you can configuration for the actual workpiece, plan the process and monitor it. ROS pack for the process storage, and ROS bridge for the universal communication level. And yeah, here you see the other components. In the later of the presentation, we will see a video. I hope it will start, so you will get a better picture how these things implemented. So here is some technical details of the lab setup. As I mentioned earlier, we used welding robots. Our drivers is also not compatible only with the OTC welding robots, but also with notch robots. They following a similar standard. So our lab implemented the notch robots at this demo purposes. We use the OTC TIG welding equipment, the laser scanners. We follow the process with the IP camera from Cisco. And the client is a Samsung Galaxy Tab. So I hope we can start the video. So here you saw the planner module. You can monitor the main the process in the picture, and you can set up the welding parameters and also follow the process on the bottom part. And this is this small setup that we prepared for the demo purpose. Our goal to be able to use it in more complex shapes, because, for example, the welding of hydropower turbine, its shape of the blades are much more complicated than a straight line. But here you see the general proof of concept of the process. I think that the video was ended. Yes. So how is the project looks like? We set up 3 milestones. We finished milestone 1, which was the main part of the development. This was the part of the integration of the software modules, the drivers, and the setup of the project, and also committing the code to the ROS community. Second milestone is the multi-pass blender module, which we are still developing. This part is could be replaceable by the parties, but our solution is might not be totally open source. We are still considering how much we can utilize here, but we will do our best of effort to share as much as is possible. And it's already about to finish. And milestone 3 is the implementation of the demonstration cells at our partners at Rainpower and at Mill, which means we are still negotiating some technical details, and please stay tuned on the updates about it. So we will come in back soon. Thank you very much for your attention. If you have questions, please ask now, or please contact the person. He's the contact person for the project.
All right. Well, thank you guys. I appreciate you guys pulling the material together, and thanks to PPM Robotics for their contributions to ROSWeld. Are there any questions for Csongor or the PPM team?
Can you hear me?
Yes.
Yes.
Hello? Yeah. So hello, I'm Gauthier Hens from Fraunhofer IPA. So we're also part of the ROS-I consortium, and we are also working in welding. And so I had some questions about. So first, your collision avoidance functionalities. So you said you used MoveIt to do the collision avoidance, and I would like to know what exactly, what for collisions are you avoiding? Are you avoiding collisions during welding, or like in the free space between weld seams, or what exactly are you using MoveIt for?
So we using not avoidance, we use collision detection.
Okay.
I would say it's a bit different concept. So during the planning, we use the MoveIt mode. So we have to handle by manually provide the path to avoid the collisions itself. But during the simulation, we would see if there are any collision. We have some troubles to implement the automatic collision avoidance. So due to the time constraints, we decided to enable it manually. And we are using not manually, but a CAM-based pass for the robot to perform the welding process itself. But I think automatic collision avoidance would be part of milestone 2 when we integrate it in the multi-pass planner, hopefully. But
so what you basically do is you program weld sim offline in the simulation by clicking on the CAD or something like this?
No, we are able to load a welding pass into the simulation environment and also to the framework. Then when we have the welding pass, which should be exported from a CAD model. And normally in welding, you requires to know where you want to weld. So you have a predefined seam pass, I think.
Okay, yeah.
And since you have to have predefined ones, you have to fit it to your workpiece. So therefore we use a calibration module, which can be like a 3-point calibration, when you define the 3 actual points on the workpiece in the simulation environment and also on the real workpiece. Then you match together, then you have the actual workpiece geometry aligned with the simulation, and also both coordinates in the robot coordinate system itself.
Well, here you don't use a visual sensor or laser sensors. It's by touching.
It's by touching.
Yeah. Okay.
So we have a feedback on the torch itself, which is a touch sensor. So when you touch the workpiece, you will get a signal, and you know where is it.
Okay.
So we have some future plans as well. Basically, we would use this path, this uploaded path, for the laser scanner, and the lasers, and based on the scanning, we will know where to weld exactly, because we will have a groove, and we have to weld there. Therefore, we will include the laser scanner measurement to the planner, and from this data, we will automatically plan the path itself. But currently, we don't have this module.
Okay.
We are developing it. So we will use laser scanners for the planning.
Okay, and what about the multipass planning? Is it also like, do you extend the multiple paths from a preliminary?
So basically, we will read the groove, and we will fill up this groove with beads. For this, my colleague Csongor made tons of research. He's doing his PhD on robotized welding.
Still an ongoing process.
Yeah, still an ongoing process.
Okay.
And we will automatically fill up a groove with beads, basically.
Okay,
and all
so
of the data will come from the laser scanner itself.
Okay, so you will determine the geometry of the gap to be filled.
Yes.
Then generate some geometry, and then determine the path, or.
Yes.
Yes. So our research is my research is focusing on the bead geometry. So when we know the gap, what we need to fill, and also or the groove itself, and we define what parameter range we want to work during welding, we can say that, okay, please fill up the beads, and then we will generate a path pattern to fill this gap. And since we should have a model from the weld bead formations, when you will know what would be the expected shape after welding of the beads, so then you will see the curved shape, curved shapes of each weld bead. Then you will know where to expect the next bead to be placed. So we try to build up a forward feeding path planner, and then if it might run without the laser sensor also, if we have a fine-tuned version, but it can also get a feedback from the laser scanner to place the next bead on top of each others.
Okay, interesting. Yeah.
Yeah. I think you will be on the seminar on tomorrow, the day after tomorrow in Stuttgart, right?
Next. Yeah. Right.
I will visit the seminar.
You will come. Okay.
Yeah, so we can have a further discussion for this topic. I think if you're really keen on it.
Okay, perfect.